Thank you very much, Anne, for the introduction. I'm very delighted to be here to contribute to this roundtable and tell you about the growing capabilities that are offered by computer simulations to understand some of the critical limitations. Is that fine? Is it better? Okay. More? Okay, so I'll try to bend and during the talk. So what I would like to do is to provide some examples of the use of computer simulations to understand electrochemical systems with applications to fuel cell catalysis and the generation of chemical fuels through artificial photosynthesis. And I'm going to try to give you a sense of the type of developments that we need for those simulations. And without too much jargon, also tell you about the inner workings of the codes that we use and what are the frontiers in terms of using them to make relevant predictions. So before I get into the core of the topic, I'd like to first acknowledge and thank my collaborators at Penn State in Venkat Gopalan, Reshak, Susan Sinot, that their expertise has been absolutely important and instrumental in everything that I'm going to present today. I would like to thank Tito Abruna at Cornell, Craig Finney, and Betul Pamuk that also contributed to this work, and also my collaborator at EPFL, Nicola Marzari, Matteo Coccoccioni, and at Kyushu University, Kiko Sasaki. I would like also to thank the students. They're often the one that solves the tough problem that we never anticipate when we come up with research ideas. So all of this would not have been possible without their contribution. So what I would like to do now is to first step back for a moment and give a perspective on the challenge at hand. And that challenge is the problem of supplying enough energy to fulfill the need of a growing population. And so since I'm a computational person, I like to put numbers on everything. So I would like to establish a link between the depletion of energy resources to the growth of the population. And you can establish this link through a very simple equation that involves three factors. The first one is the socio-economic factor, is the GDP per capita. It's one measure of the activity of the economy on a per capita basis. The energy intensity is the second factor that really tells you how much energy you need to produce $1 of GDP. And the last one is what is called the extraction intensity. That is how much gasoline, how much coal you need to extract from the ground to produce 1 unit of energy. And so now you can look at statistics from the World Bank and other sources. And the statistics tell you that the population of the globe increases at 1% per year. So this seems very small, but this means really that over the last 20 years, we have added more than 1 million people on the world population. The economy is very active and the GDP per capita increases. So this is great news for the economy, but not so great news for the consumption of energy resources. Fortunately, the energy intensity, thanks to technological progress, decreases at the rate of 1.5% per year globally. But this means that we're still left with 2% of systematic increase in the consumption of fossil fuels. And so the only hope that we have really is to decrease the extraction intensity at a rate of at least 2% per year. And this means that we need to be able to introduce renewables in the energy mix at a rate that is greater than 2% per year. So this is really the number that we need to keep in mind when we talk about energy sustainability. It's certainly a difficult challenge, but I would like to show that probably this is not impossible to achieve. So we have reasons to be optimistic. For example, if you look at the transportation sector over the last 20 years, there has been a gradual adoption in hybrids. Nowadays, we're also seeing an increasing affordability of electric plug-in vehicles. And because of this combined effect, there is now a clear inflection in the consumption of fuels. So this is really a positive sign that shows that through technological change, through the effort of scientists and engineers, there is a way to essentially curtail and to overcome some of the important challenges related to energy consumption. But this optimistic picture does not take into account an important contribution, that is the contribution from heavy-duty vehicles like large trucks, like large ships and large aircraft that still contribute more than 40% of the energy consumption. And this share is increasing over time because we don't have right now sustainable electrical alternative to those heavy-duty vehicles. And so this is because batteries and capacitors nowadays do not have sufficient performance in terms of energy density and power density to provide energy to propel those kind of heavy-duty vehicles. So for a long time, we'll still need to find ways to essentially produce chemical fuels for those large heavy-duty vehicles. And the question is, how can you produce those chemical fuels in a sustainable manner using limited carbon resources? And one answer is artificial photosynthesis that consists of mimicking the process uses that plants use in order to produce organic nutrients. And using artificial photosynthesis, you can see that different fuels can be made. You can produce methane by combining CO2 and water under sunlight. You can also vary the stoichiometric amount of CO2 and water that you have. And in that way, you can produce more complex hydrocarbons such as alcohols. But perhaps the most interesting fuel, perhaps from the point of view of its relative simplicity and its energy content, is hydrogen that can be produced by the water splitting reaction. So this is a reaction that can be promoted in different ways. For example, you can promote it at the surface of a photocatalytic conductor, and this photocatalytic conductor needs to fulfill different requirements. The first one is that it needs to be compatible with the solar spectrum, so it needs to absorb solar photons to generate a pair of electron and hole. Then there needs to be a driving force to separate those excited charges in order to bring the electron on the electron accepting side, where it's going to promote the catalytic reduction of protons, and on the other side, the electron donating side that is going to enable the catalytic oxidation of hydrogen, of water into hydrogen. And so once you have this hydrogen, the process can be reverted into a fuel cell where you can extract the electron from the hydrogen fuel and extract it and send it to an external circuit where it's going to power the external device. And then the electron is going to come on the other side to recombine with a proton and an oxygen that is waiting on the electron accepting side of the circuit. And so as long as you have sunlight, this process can be continued forever, and this really makes hydrogen an ideal energy carrier for this type of reaction. And so what I would like to do today is to explain the role of simulations in order to understand and to predict the performance of this type of systems. I'm going to start with a fuel cell and talk about the issue of durability. So this is something that Mark alluded to previously. And for many of the fuel cells, the critical limitation is the fact that the voltage window is restricted because we don't want to induce catalytic dissolution of the electrocatalyst. And you can see here a cyclic voltammogram where you can see that if you have small nanoparticles and if you have a large voltage window, what's going to happen is that you're going to induce the rapid dissolution of the catalyst that is going to decrease the catalytic activity of your fuel cell. And so if you want to simulate this process, if you want to understand the microscopic mechanisms on this process, you need to simulate what we alluded to several times previously, that is the electrical Dabo layer. So this is a schematic of this electrical Dabo layer. I take here the example of a copper-covered gold electrode. And what we would like to do is to understand the effect of the voltage on the catalytic dissolution and on the restructuring of the interface. And so the voltage is nothing else than the difference between the chemical potential of an electron inside the electrode, that is the Fermi energy, and the long-range value of the potential inside the electrolyte. So this is one working definition for the voltage. And as you increase the voltage, you're going to shift down the Fermi energy, rendering the surface positive, and this is going to be compensated by the accumulation of negative electrons, negative ions at the interface. And you can see that this Dabo layer, this capacitive Dabo layer, generates an electric field, as you can see from the sharp decay of the potential. So what we would like to simulate is what is the effect of this voltage on the surface states and the dissolution process. And to understand this, you can realize that as you increase the voltage, what's going to happen is that you're going to decrease the amount of electronic charge that enables the binding between the ions inside the electrode. So the nuclei are going to be less bonded. And at some point, one of the nuclei is going to say, I don't have enough here to hold me, and I'm going to feel happier if I jump inside the solution. And this is a typical process that requires you to understand the effect of the voltage. So it's fundamentally quantum mechanical because you need to understand the effect of the macroscopic voltage on the chemical potential of the electron and what is the effect of the electrochemical potential on the binding between the nuclei that form the electrode. So you could tackle this problem by using first principle molecular dynamics, but this tends to be very expensive very quickly. And so what we would like to ask is, if you don't have sufficient computational resources, what type of method is left to you in order to simulate this type of process? And for this, we can resort to so-called quantum continuum embedding method, in which you substitute the complexity of the dynamics of the solvent, where you have to solve Newton's equation and propagate them in time and calculate at each time step the forces that act on the nuclei, by the simplicity and the representation of the solvent that can be described by a continuum dielectric. You can see here the red and the blue density that surround the electrode that represent the average position of the hydrogen and oxygen from the water molecule. And this is there to mimic the effect of the polarization of the solvent that is going to stabilize different intermediates at the surface. So you can do that by including also some water molecule at the surface. And you can see that you can apply this not only to surfaces that are made of metal oxide, metallic electrode, but also quantum nanoparticles. And so what we did is to apply this type of techniques to be able to understand the effect of the voltage on the dissolution process. And this is, for example, something that can be used to understand and predict which site on a different nanoparticle of different size and shape is going to be the most susceptible to electrodissolution. So this is an example. We obtain here the dissolution energy as a function of the voltage, including this stabilization effect of the solvent. And what we realize is that, contrary to intuition, it's not necessarily the least coordinated site that is going to dissolve first. You can see here this crossing that is induced by the interaction of the surface dipole with the voltage that essentially leads to the preferential dissolution of the metal on the 1,0,0 facet, as opposed to the corner site that should be less coordinated and that you would think will try to dissolve first. But because of the interaction of the solvent in that electrical double layer, what might happen is that you have a preferential dissolution that does not follow the coordination trend. Another example of interest to fuel cell catalyst, for example, this bimetallic subsurface alloy is a promising and very attractive way to boost the catalytic performance of different electrode materials. And you can see here that, again, by including the effect of the voltage, we can predict the restructuring of the electrode using Monte Carlo cluster expansion techniques that are parameterized using those first principle simulation under applied voltage. We can understand that as you increase the voltage from the left to the right, you have a gradual enhancement of the population of trimer, and then you have a non-monotonic trend that leads then to the emergence again of monomers. But you can see also that you have an enhancement in the population of the multimers, and you can see here, for example, different rings that form under high voltage that may have an important contribution to the electrocatalytic activity of this type of surfaces. Beyond this, we would like to also continue to develop this type of model to be able to look at more complex catalysts. For example, combining the complexity of nanoparticle with that of bimetallic electrodes, it will be possible to study the stability of more complex bimetallic nanoparticles. And this is something that is done as part of this DOE-funded project by the CPIMS program, in which we would like to increase the complexity of the type of catalyst that we can study on a regular basis using this type of quantum continuum model. And ultimately, I think it will be very interesting to understand the formation of more exotic nanoparticles that are shape-controlled, for example, those platinum and nickel nanoframes that show extremely good performance in terms of catalysis, but for which there has been limited studies at the first principle level in terms of their catalytic durability. So this is something that requires you to understand the effect of the double layer, and this is the type of work that I think is at the frontier of what can be done right now, and for which there should be effort trying to understand the double layer and couple that to detailed first principle simulations. So now I would like to switch gear and tell you about another aspect of the work, not on the fuel cell, but on the photocatalyst. And as often in this type of energy conversion system, the bottleneck is the material. And we would like to use computer simulations to accelerate the screening of materials for water splitting. And this is a difficult problem, but thanks to the evolution of computational capabilities, it is now possible to predict many of the fundamental properties that contribute to the performance of a photocatalyst from first principle. And so if you think about the water splitting photocatalyst, there are several requirements. One of them is the catalytic stability. So you need the catalyst to be stable under a self-decomposition. So essentially you need the energy of self-decomposition to be always equal to zero, meaning that your compound must be on the convex hull that corresponds to the most stable elements as a function of composition. And you also need to have a band gap that matches the solar spectrum. And you need also to have good band alignment between the redox potential of your photocatalyst and the redox potential for hydrogen reduction and water oxidation. So once you have those criteria, you can think, since I can calculate them systematically for many materials, what I could do is essentially go in the computer and start from a long list of compounds and gradually narrow down the choices by eliminating the compounds that do not fulfill a given criterion. And this is certainly doable, but the success of this type of approach depends obviously on the accuracy of the method that you use. And this is why it's important to have a good understanding of the trade-off that you make when you apply this type of first principle method. So what I would like to briefly do is to explain the type of trade-off that you make when you apply a method like DFT. So in DFT, you substitute the complexity of the many-body wave function into the simplicity of a description that depends only on the charge density. And instead of having the many-body Hamiltonian, you will have a one-body Hamiltonian that depends on the charge density. So this means that you need to solve this equation self-consistently. You calculate the charge density, then you calculate the effective Hamiltonian, and then calculate the orbitals, and you perform this loop. So when you perform this type of simplification, there's something unphysical that happens, that an electron, because it contributes to its density, to the total density, it will contribute also to the potential that acts on itself. And because of that, electrons can feel the interaction with their own image in density functional theory, and this tends to lead to a phenomenon called self-interaction, whereby an electron will repel itself and be less stable than expected if you were to do the full many-body calculation. And this is clearly seen when you compare computational band gaps to experimental band gaps, where you can see that in DFT it's too easy to excite an electron because it's already destabilized by its interaction with its own field. So what you can do to overcome this limitation is to not only build the potential in terms of the charge density, but also in terms of the orbital itself. So what you do, you calculate the potential, but you subtract the contribution from the orbital of interest, and in that way you can see that you get much better agreement between experiment and theory. This tends to be, unfortunately, very computationally expensive, and so there needs to be ways in which you can break down the complexity of this type of calculation, and this can be done, for example, by retaining only information about not the charge, not the orbital itself, but about the symmetry of the orbital. So for different orbital angular momentum channel, you're going to have a different potential, and this enables you to correct this tendency for self-interaction and self-excitation of the electron by using a method that is less computationally demanding than the full-blown orbital-dependent prediction that I showed. So this is the type of prediction that you can obtain using that, and you can see that in most of the case we get good agreement, or we tend to overestimate the bandage position so that you can get a good essentially window of upper and lower bound if you use the vanilla DFT and this angular momentum resolved DFT. And so based on this, you can have a solid basis to do your screening. Then we also ask our experimental colleagues very early on which candidates can be made, which material can be made, and they went through the literature and essentially for each of the material of interest determine whether or not there is an experimental recipe to make them so that we can restrict our search to compounds that can be made. So based on this, you can have this now screening protocol whereby you recognize the limitation of vanilla DFT, the one in which you take into account the density to calculate the potential. And there you basically extend your criteria so that, for example, you don't restrict yourself to band gaps of 1.5 and 3, but you go from 0.5 to 4. Then you calculate the band edges. You then go to your experimental colleagues to check the abundant toxicity and the ability to synthesize the compound. And then you do the refined DFT calculation on the 258 compounds that remain, and we ended up with 30 compounds at the end of the day. So does this work? So 12 of the 30 compounds have been made successfully so far with high purity. So you see the XRD patterns that are in good agreement between experiment and theory. And then they were tested photocatalytically. So this is a tremendous endeavor that was carried out by Kathy Badding in the group of Titra Brunia. And she also did an internship over the summer at NREL to use state-of-the-art photoelectrochemical characterization techniques to determine the band alignment of those compounds. And they all show promising band alignment. But the most important result is really this one, where it ultimately, using gas chromatography, we show that 7 of the 12 compounds that were made show actually this peak in the photocatalytic activity towards water splitting. And we were extremely thrilled and very excited by those results because it really shows that by this collaboration between experiment and theory, and by paying attention to the approximation that you make and the trade-off that you make in your calculation, you can make some progress in the development of new photocatalysts. But this is not the end of the story, because you can see that some of the compounds that we predicted do not show any peak. And so this is something that means that we need to refine our predictions and refine our screening criteria. For example, some of the limiting factors that we didn't take into account are charge separation. So the second step, what is the driving force for separating the electron and the hole, and what is the influence of surface structure and the absorption of different adsorbates on this driving force that we call the Schottky barrier, and also the surface activity. We didn't say anything about surface activity, and this is certainly something that needs to be included in the screening criteria. So with that, I would like to conclude. So I hope that I was able to give you some example without too much jargon of the usefulness and the capabilities that can be used in order to predict the stability, let's say, of catalytic nanoparticles and also bimetallic surfaces, showing that clustering tendency as a function of voltage. And I'm also very excited about this work that is funded by the DMREF Infuse program that really enables us to discuss with experimentalists and have this cycle of interaction whereby we can determine new photocatalysts and test them experimentally and then refine the accuracy of our computational predictions. So with that, I would like to thank you for your attention, and I'll be happy to take your questions.
Time for questions?
So I'm Laura Gagliardi. Thank you very much. It was very beautiful. So concerning the second part about the challenge of predicting the right band gap in these materials, so of course there have been other approaches historically, like the plus U parameter that was developed in your group, or working with hybrid functionals. But the problem is that, for example, if you don't know the answer ahead of time, maybe you cannot be predictive because you use a certain U for a certain metal, but what if you have a different composition of your material? So how does your approach work in this respect? How does it compare with these other methods?
Yeah, so the approach that I've shown, that some of the results that I've shown there actually, so this is a LDA plus U that is applied on different orbital angular momenta. And the difference is that this is a linear response. GGA plus U. DFT plus U. Absolutely, yes. So this is a GGA plus U in which you use linear response theory to calculate the parameters, and you can do that in an efficient way using new implementations that really push the limit of those techniques. But as you can see, as you said, you really need to test your result to get experiment and get a sense of whether or not you can trust it and what is the trend that you obtain. So what we see here is that we tend to overestimate the band gap using this technique, and as opposed to the DFT that the regular DFT without the U, the semi-local or the local DFT that underestimate the band gap. And here, what we found is that most of the cases, let's say in 6 times out of 10, you will find yourself in this situation. And so based on this, once you understand this, you can then use that as your screening criteria. But the problem is still not solved. I mean, we still need to find this balance between computational cost and accuracy. And this is where the contribution and the interaction with experimentalists is extremely important. You need to have good benchmarks on which you can validate your method. And this is, I think, something that can really help the development and the understanding of the performance of those techniques.
Hi, 2 things. You talked about stability. There's both thermodynamic stability, which of course is very tough for many of these, but then there's also some kinetic stability, and whether you had some ideas on how to bring that into your design concepts. And then the other thing that a lot of people often run into is you can get the band gap, you can get the band edge. It's actually getting it to conduct properly. And so thinking of doping mechanisms and what you can do theoretically there, of course, is another important element. Wondered if you would want to comment on kinetic stability and then how you might handle transport and getting the right level of conductivity through understanding doping and defects and things.
Yes, so I mean, the issue of kinetics is absolutely important, and this is also what I alluded to at the end of the talk, that you can predict a lot of thermodynamic trends, but the kinetics needs to be taken into account to understand the activities. There are relations between thermodynamics and kinetics in terms of scaling relations, but it's always something that needs to be considered. So the way we address it here is by combining our predictions from DFT to molecular dynamics simulation. So I work with a group of Dr. Susan Sinott at Penn State, where she uses a reactive force field that enable us to tackle a system size that are much bigger than that. And there we really explicitly look at the process of the effect of the voltage in real time on the dissolution process, and we learn a lot of things. But even there, the timescale that you can achieve is not always sufficient for the type of process that you want to do. So this is something that you could think to tackle using kinetic Monte Carlo, but this is something that is much more computationally demanding than the method that are presented here. Regarding the issue of the charge transport, this is indeed something that we hope to be able to address, and this is related to the driving force that exists in the depletion layer of the semiconductor. So this is one aspect, but also the polaronic mobility is something that more and more people are looking at, and understanding what is the energy barriers for a localized charge to hop into a semiconductor in an oxide is something that a lot of people are looking at right now. So this is totally fair comments. Kinetics is absolutely important and at the frontier of what we're trying to do at this moment.
Any other questions? Let us take Ismaila.